Well, greetings and good morning, everybody. Happy Tuesday. Welcome to another session in Engineering 260. You should be seeing my screen at this point, and we are going to pick up our conversation on op-amp circuits. And last we left off, we actually went through the derivation for a couple of we talked about amplifiers in general. We talked about loading amplifiers and input and output loading and things like that. Ideal versus non-ideal amplifiers, assumptions we can make to real amplifiers that allow us to use ideal techniques, which really simplifies the analysis. And we arrived at those golden rules of the op-amp, namely that the inputs don't draw any current, and the op-amp action is such that the second rule is that the op-amp action dictates that the op-amp will do whatever it has to make the two input voltages, Vn and Vp, identical to one another. Okay, how does it do that? It pushes current out of the output pin, or it pulls current into the output pin to drive the voltages equal to one another through the feedback path, which is it's typically connected to the inverting terminal, the negative terminal. And there are cases where you can use positive feedback, but we'll save that for another discussion if we even get to it. And in that, we covered, we derived the formulas and the response and the behavior of a few very common op-amp circuit blocks. And one of the things, we did that for kind of two reasons. One was to show how to apply the golden rules to analyze op-amps and then derive the relationship for something that you don't know how the op-amp works. And the second reason we're going through this is so that you can see these common op-amp blocks and then start to recognize and pick those out when you see a circuit with various op-amp blocks. You can then apply, once you know the behavior for that circuit, you can apply the input-output response that you already know, that we've already derived. And so the op-amp blocks that we've done up until this point in the course, we covered last week, were the voltage follower, or the buffer, as it's called. Remember, that just gives you whatever voltage you put into the non-inverting input, it gives you out at the output. The inverting amplifier, which inverts a signal, and it gives you gain, and the non-inverting amplifier. Okay, now if you wanted to review those, well, let's go review those in just a moment, okay? Let me just, in terms of leading towards announcements for today of what we're going to cover, we are going to look into a couple of other, we're going to derive the response for a few other op-amp blocks, namely the current to voltage converter. Can I spell here? There we go, converter. Or an I to V converter. We're also going to look at the summing amplifier. And then there's also a difference amplifier or differential amplifier. But I want you guys to watch this on Canvas, or watch the pre-recorded videos on Canvas. I've put a link to those in the modules section. So that brings me towards announcements. And let's see if I pull up there we go. So if you click in the modules section here, if you click the link below, there's a link to op-amp videos. It says differential amplifier and cascaded op-amp example. So that'll bring you to this page, which has a few tabs. The tabs 3 and 4 are empty. I've not put videos there, but tab 1 has videos on differential amplifiers. And this will lead you through the discussion.
Okay, folks, welcome back to Engineering 260.
You know what? It looks like that is
circuit with inputs V1 and V2. Welcome back to Engineering 260.
Yeah, so I see. So this is actually a video on an example. So what we'll do is we'll cover the differential amplifier in class today, and then I'd like you to watch some pre-recorded videos on Canvas which go through the analysis. Okay, and then finally we'll talk about cascaded amplifiers. Okay, and hopefully we'll have time to get to that. That said, other announcements, real quick. You will see shortly, I will post a link to a supplemental homework assignment on op amps. I've seen some of you have started or even finished the op amp homework on WebAssign. I'll likely extend that because I think some people need a little bit more time. I think it was due on Thursday or Friday. I'll push it into Sunday. I am going to post that other homework later today. I'll send out an email when it goes live. You'll see it here, and they're more challenging op amp problems than what is in the WebAssign assignment. Okay, a couple other announcements. It was brought to my attention recently that the video lesson number 2 for Thevenin's theorem, which we talked about in Norton's circuits, was cut off, unfortunately, at about 27 minutes. I have no idea what happened. I know we did the whole video session, and I think Zoom just somehow dropped the rest of the file. So I'm really sorry about that. There are the notes that are available there. I don't have that lesson recorded in some other format from another time or anything. So if you need to catch up about that, please do check that out. Also, one other item is that there's been some interest expressed in doing some practice study sessions. And I believe that on the Discord channel soon, it doesn't look like it's there yet, but or if it is, I'm just not seeing it. Someone's going to post a discussion about gauging interest in doing a review and practice sessions with our peer instructor. We are actually hiring a second peer instructor right now. His name is John. We're getting him onboarded this week, so we'll get you set up with his hours as soon as we have those identified as well. And so either he or Guillermo could help lead practice study sessions. If you guys can paste into the chat on Discord what topics you would like to review, then they can. The discussion's on Canvas. Thank you. Thanks, Michael. So thank you. So it looks like there's a discussion going on Canvas, extra practice sessions. And so it looks like, Michael, thanks for getting this started. And it looks like it's looking for a time for that would be a good meeting time. And so please go ahead and check out the doodle schedule there. The PI, Guillermo or John may be able to help. And actually, and so we hopefully try to set up something weekly that they can facilitate. But I'd be happy to come in and do some, either join those periodically or do another one at some time where it's just us or however. So I just want to make sure that you're getting the opportunity to get the practice. I know that these problems are getting harder and harder. The analysis is getting more involved. Keep in mind the mathematics are usually not the linchpin here. A lot of times it's conceptually what's going on in terms of op amps, like using the rules and knowing where to apply them. So I'd like to continue modeling what that how to be intuitive and use the rules and see things a little more easily, because it can be very easy to get, especially as you're a new player in the scene and working in circuits and stuff, can be very easy to not see things, you know, as clearly because you haven't had as much practice looking at them. So I'd really love to spend some time working on that with you. All right. I think those are all of my announcements. Oh, my last announcement is that reminder that there's no class on Thursday. Thursday is in fact a flex day. So hopefully we get through the rest of the op-amp discussion today. We'll see how we do. All right, so let's then jump back in. As a reminder, we talked about these golden op-amp rules, and then we looked at the following circuits. We looked at the voltage follower. Remember that it just gives you, it's when you apply the input to the non-inverting terminal. Let me just go full screen here. To the non-inverting terminal VP, it gives you out the same voltage that you put in. It doesn't matter, there's no voltage drop across R1 here because remember, there's zero current into the inputs. So it gives you the voltage source back with renewed sort of vigor or whatever. It can drive the current loads. We talked about the fact that it doesn't load down. It prevents loading the source down by, the load does not load down the voltage source. And that's the benefit or the virtue of the voltage follower or buffer. Now, we looked at the basic inverting amplifier. That's it there. So if you want it, I don't have enough room. One of these times I'll actually give you a sheet that shows you all of the different amplifier blocks with their names and then their behaviors on them, but we're developing them now. Let's go through and develop the whole thing, and then we can catalog all of the different amplifier types that we've encountered. So this is one of them. It was the basic inverting amplifier. We'll show this again in a moment. You'll see this come up in another problem we're going to do shortly. We have also the, remember that the inverting amplifier, the input here is applied through a resistor to the inverting terminal, and the non-inverting terminal is grounded. That's one of the key things to help you recognize an inverting amplifier block. Then there's a feedback resistor RF here. The gain is the ratio, the relationship is V out is equal to negative RF over R1, the ratio of these resistors, times VI. That negative out front is what tells you it's also, or that is also part and parcel of it being an inverting amplifier. Remember, the gain can go anywhere between 0 and theoretically infinite. We looked at what a graph would look like if you put in a sine wave into here. And this, let's say this was a 2-volt peak-to-peak signal. So it goes from plus 1 volt down to minus 1 volt in black here. And we looked at what the output of the amplifier would look like for various gain settings. Gains less than 1, gains greater than 1. Okay, then we looked at the non-inverting amplifier. Remember, how do you recognize a non-inverting amplifier? The signal is applied to the non-inverting input, VP. And you have the feedback, you still have a feedback resistor connecting the output back to VN. And you've got R1 tied down to ground. You've got another resistor tied down to ground. V out, in this case, the relationship is VI times the quantity here, 1 plus RF over R1. So the smallest the gain could ever be is actually 1. It can't be less than 1. And theoretically, it could go up to infinite, but you know, all op amps have limitations. Okay, so now let's take a look at a circuit that this op amp here, if we look at the way this is configured, this op amp is neither an inverting amplifier block or a non-inverting amplifier block because there are 2 signals. There's a 6-volt source connected to through a 20K resistor to the inverting terminal here. And then there's a 2-volt source connected to the non-inverting terminal there. So it's like, is this a non-inverting amplifier or is it inverting amplifier? Well, it's neither one independently. And so we're going to solve it that way. But what we'll see is that there are a couple different ways you could solve this. And one of them is that you could treat this as which we'll come back to later, you could look at it in terms of superposition of two amplifier blocks, excuse me, by turning off each of these sources. But we'll look at that shortly. For now, let's pretend we don't know how to apply that, any of those procedures. And all we're going to do is then just apply the golden rules. So keep those in mind. Remember, number one is that IN equals IP equals 0. And then number two is that VN, the op amp will do whatever it has to do to make VN equal to VP. So if that's the case, let's go ahead and do a nodal analysis at VN. This is VN here. Okay, one thing I actually want to point out before I move any further is what if we did nodal analysis at Vout? It could be tempting if you had like a load resistor right here, let's say, and you thought, oh, I want to do nodal analysis at Vout. Then maybe you do something like, so just as a disclaimer, this is we're covering this so I can. We can discuss why never to do this. Don't ever do nodal analysis at Vout. And here's the reason. Maybe you'd say if this node is Vout, then you've got a, let's say if you're doing far minus near, you've got a 0 minus Vout over RL plus a VN, this path here, minus Vout over 40K is all equal to 0, right? Well, not quite, because that accounts for the current coming up through RL and the current through this 40K, but what about the current through, remember the op amp has supply pins, plus VS and minus VS, and it can source current out of that output pin, or it can sink current into it. So you actually have an I out here, plus I out. Now that all that is equal to 0. The problem here, the reason that this is such a problem is, remember that by op amp rule number 2, the op amp will provide whatever current is necessary, I out, to keep VN equal to VP. So you can't know what I out is. This equation doesn't get us anything useful at all, unless somehow you already knew I out. But remember, the amplifier will just provide whatever is needed. So for that reason, don't ever do nodal analysis at the output pin of any op amp, even if you have a circuit with multiple op amps throughout. Never do a nodal equation at the output pin to figure out what the relationship is. If you wanted to find out the output current in or out of an op amp, and you already know the other voltages in the circuit, like you already figured out kind of the other stuff in the circuit, and now you want to go and answer the question, okay, how much output current is coming out of or going into the output of the amplifier, then you can go and do a KCL at that point in the circuit. But don't ever do nodal analysis as a starting point to find it, because you just don't know the current in or out of the output of the amplifier, and it's too much of an unknown. All right, so with that said, that bit of discussion there, we are going to go and look at the output, or do a nodal analysis at VN, okay? So what we've got then is we've got the current coming through here. Let's go back over to my blue ink here. We've got the current coming through that 20K. We're just going to call this VI, I guess. We're going to call this V2 for whatever reason. Let's just call this V1. I'd rather call this V1. Let's call this V1 and call that V2. And so we've got the current coming through the 20K. That's a V1 minus VN all over 20K. We've got the current through the 40K resistor there. That's a V out minus VN over 40K. And all of that is equal to 0. Now, What we notice though is that Vn, remember the op amp is going to do whatever it has to make Vn equal to Vp. Vp has been connected to a 2-volt source, which makes Vn equal to 2 volts. More generally, what we can just say is it is equal to V2. And so, so let's go ahead and write this in here. We'll just say that, you know, if we wanted to just draw a note on here that Vn is equal to V2, and this is by rule number 2. So what we can do then is we'll write this as V1 minus V2 over 20K plus a V out minus V2 over 20K. Oh, sorry, over 40K. And in fact, you know what? Here's what I'm going to do. I'm going to write this in terms of R1 and RF, because the 20K is R1, the 40K is RF. And what I'd like to now do is then, oh, whoops, this is all equal to 0 here. What I'd like to now do is then multiply this whole thing by R1 times RF, common denominator there. And what we're going to do is arrive at a general relationship here. So we get then that this would be an RF times V1 minus V2 is equal to an R1 times V2 minus V naught. Okay, so all I did was take this term here. That was a V naught minus V2. And I moved it to the other side so that the order changed. So it's V2 minus V naught. All right. And so if we then collect terms for V naught, we get a minus R1 V naught is equal to RF times V1 plus, minus RF times V2 minus R1 times V2. All right, and if I then go ahead and divide through by negative R1 on the other side, I'm gonna on both sides, we get that V out is equal to minus RF over R1 times V1 plus V2 times 1 plus RF over R1. Okay, so that's the general formula for this amplifier. Notice that it's neither an inverting amplifier or a non-inverting amplifier. However, if you look at it in the form that we've just arrived at, it looks like these two terms look pretty similar to things we've seen before. Is this a non-inverting? And is this, oh, sorry, whoops, that'd be inverting, right? And is this a non-inverting? Those really look similar to those equations. And in fact, that is exactly the case. And in a moment, we're going to solve this circuit now by plugging in numbers for RF, R1, V1, and V2 in just a second. And we'll get a numeric value for V out. But on the next slide, we'll go ahead and do this problem again using superposition and our common op-amp blocks to do this an easier way. Well, at least I think it's an easier way, because then we're not having to do nodal analysis and, you know, carry through a bunch of algebra. If we already know how these amplifier blocks work, we can actually just sum their responses using the superposition principle and get the same result. All right, so so if I then plug in, let's say I come over here and I'll plug in numbers for V out. So V out is, it's a negative RF over R1, so negative 40 over 20 times the V1, which is 6 volts, plus V2, which is 2 volts. Put units on here. 2 volts times, this is 1 plus, again, it's RF over R1, 40 over 20. So that's a negative, what is this? Negative 2 times 6 plus 2 times, what is that, 3? So we're getting, this is negative 12 volts plus 6 volts. The whole thing then is V out is equal to negative 6 volts. Okay. So we were presented with a circuit that is neither, it's not a common op-amp block as it stands written on paper or as it's shown here. And so anytime you're presented with something that is not a common op-amp block and you're not able to reduce it down to common op-amp blocks through superposition, which we'll do shortly, but sometimes you can't do that, then you have to start with, from the basics with the golden rules. Input currents the inputs draw zero current, and the amplifier will do whatever it has to force the voltages equal to one another. The input voltages, Vn and Vp. Okay, so we solved the circuit using that technique. So let's then go ahead and now do it again, this time by using the superposition principle and common op-amp blocks. So what I'd like to do, and now this will be a chance for us
to go back to your previous slide real quick.
Yes, sure.
Just real quick.
Yep, thanks, Jose.
Thank you.
Before we, while we're on this slide, before we go on to look at this in terms of superposition, does anyone have any questions on steps that we went through, simplifications made, anything I can help clarify? Okay, so then let's go ahead and take a look at it, doing it again on this, using superposition and common op-amp blocks. So what, using superposition, remember the superposition principle, we turn off all but one source at a time. So first, we're going to find, so basically, here's what we're going to do. We're going to find V out total as V out due to the 6-volt source plus V out due to the 2-volt source. Okay, and all we need to do is find out what the formulas for those are. All right, so let's find the formula of V out due to the 6-volt source. Okay, so when we redraw the circuit by turning off that other source, here's what I'll put in. So this is whoops, hang on there. Sorry about that. So here's V1. Remember, this is V1 and this is V2. V2 connected to the non-inverting terminal has been grounded. And then we still have the feedback resistor connected to connecting Vn and V out. So here's RF and here's R1. When we look at it that way, we can see clearly that this is an inverting amplifier. And therefore, we actually already know what V out due to the 6-volt source is. This is minus RF over R1 times V1. All right, so this is one of the nice things about, you've learned the superposition principle earlier in the course, and now we're applying it to amplifiers. And what we're seeing is when we turn off, in this case, we turned off the 2-volt source, V2, this circuit reduced down to a common op-amp block that we do know. And therefore, we don't have to do any nodal analysis and use the golden rules. We can actually just use the behavior, the formula, the relationship for the inverting amplifier we've already derived, and there it is. Okay, so now let's do, so that was finding V out due to the 6-volt source. let's find V out due to the 2-volt source. All right, so we'll redraw the circuit so it's nice and clear. Here's the amplifier. This time the 2-volt source is connected here. So I'm just going to show this as V2. Here's here's R1. Here's RF still connecting the output to VN. And V2 has been grounded. So now it's been turned off. So now we see that R1 is grounded. And when we look at the amplifier in this configuration, we recognize this as a non-inverting amplifier block. And we already know the formula for a non-inverting amplifier block. It is always, it's the inverting voltage, V2 in this case. It's the voltage connected to the non-inverting terminal times 1 plus RF over R1. All right, so then if we go ahead and then plug in those expressions, now that we have the expression for V out due to the 6-volt source and V out due to the 2-volt source, we can now plug those in, that this is minus RF over R1 times V1 plus 1 plus RF, or I'll just write it the other way, I guess. This is V2 times 1 plus RF over R1. Okay, that's the same exact formula we arrived at starting this with basic principles. Okay, so there you have it, and we could plug the numbers in, we get the same value. It's minus 6 volts. All right, let's take a look at another example. Now here's an example. Now this is not a common op-amp block. We're seeing something that this doesn't look like just an inverting amplifier or a non-inverting amplifier. However, we can start to simplify some things using the golden rules to kind of convince ourselves that this is in fact a common op-amp block. We just didn't see it as such. It doesn't look like it is at first glance. But let's go ahead and start off by, let's just think about the golden rules for a second here. Before we go through and start to analyze, rule number 1 says that the input currents are 0. That actually helps us out quite a bit, because what that says is that there's no current through here. That this is 0 amps going this way, which then means, so like if we knew VP here, that would be helpful, right? But if there's 0 current going into the input of the non-inverting terminal, VP, then that means all the current through the 3-volt source is going through this 4K and 8K pair. And that makes a classic circuit we've seen and we always love to use anytime we can because it's so easy to calculate. It makes a voltage divider. So VP then by voltage divider action, so you know, since IP is equal to 0, therefore you can calculate VP as, well, it's 3 volts times 8K. Well, we'll just leave the K off, right? 8 over 8 plus 4. That's 8 twelfths is 2/3, right? So then this is 2 volts. So VP is 2 volts. So what we've then just figured out is the following. We can actually, there's a couple ways you could go and solve this. Once you know VP is 2 volts, I'll just show you a couple ways you could solve this. all right? Like we could just use the golden rules and then get there, or we could recognize that this is a common op-amp block. Essentially, we have 2 volts feeding the non-inverting terminal of an op-amp. And take a look, we've got a feedback resistor RF 5K between the output and the inverting terminal. And we've got the inverting terminal connected down to ground through a 2K resistor. Well, that is a non-inverting amplifier, okay? So if you wanted to, what you could do is then at this stage, we'll solve this 2 ways, right? Okay, let's take a look at, hold on here. But this thing here, this is, if we redraw this, sorry here. Not drawing my op amps very well today. That this, if we redraw the amplifier, we have 2 volts going into the inverting, the non-inverting terminal, and we've got a 2K and a 5K resistor right here. And so this is a non-inverting, this block is a non-inverting amplifier. And so you could just then go ahead and use the formula. It's going to be the input voltage, that voltage provided to the non-inverting terminal, times, remember it's 1 plus RF over R1, or that's 2 volts times 1 plus 5K over 2K, which is 5 over 2 is 2.5. So that's 2 volts times 3.5, which is equal to 7 volts. Okay, so the answer is that this is 7 volts. Okay, that's the answer to, that's the output voltage, the out. Well, let's talk about another way you could go about this. Now, before I talk about this, for me, the way we just did it is how I think about it, is how I would approach this problem. It's once you know and you recognize that 3 volt source with the 4K and the 8K is just a voltage divider, and it's giving you 2 volts to the non-inverting terminal. Just use this, just recognize it as, okay, that's a non-inverting amplifier block. I'll just use the formula and quickly calculate what the output voltage is. Now you could go another way. You could use rule number 2. And you say that VP is equal to VN, which is then 2 volts. So you could say, oh, okay, well here, this is 2 volts. If I know that that's 2 volts, you could then immediately then go and look here and say, okay, that's 2 volts divided by a 2 kilo ohm resistor. That must be 1 milliamp of current flowing through there, right? 2 volts divided by 2 kilo ohms is 1 milliamp of current. There's no current into or out of the inverting terminal. So then there must be 1 milliamp of current flowing through here, which would then indicate, if that's 1 milliamp of current across a feedback resistor of 5 kilo ohms, 1 milliamp times 5 kilo ohms is going to give you a 5 volt drop across that feedback resistor RF, which then if you take the 2 volts here, you do a mini KVL, 2 volts plus 5 volts gets you to your 7 volts at the output. Okay, so that way, the second way is a little bit more familiar towards just how we've been analyzing resistive circuits and doing, mini KVLs and like a walk across some, across a segment of a circuit, and just looking at currents and voltage drops and building up to the answer. The first way we approached it is the more a block-oriented way, intuitive way to approach this. Now that you recognize the op amp as that block, just let all that circuit analysis that we just did with the 1 milliamp of current and then finding out some voltages, letting VP equal to VN, just let the op amp abstract all those details away. And now you already know what, you don't need to work. I mean, if you need to go and find those currents, then that's okay, and go find them. But if all you're looking for is the output voltage, use the non-inverting block. Okay, let's then go through and take a look at another amplifier block called the current to voltage converter. It's a pretty simple one, honestly. If you've got a current source, you can turn it into a voltage source by using an op amp. And so if you had set this up and you wanted to find out the output voltage V out, well, all of the current, we know that this is 0 volts by the op amp action. Vn is going to be equal to Vp. And then all of this current is going to flow through the feedback resistor. And it is actually going to be, so if you looked at V out and you just did a nodal equation here, you know that it's going to be 0 volts minus the drop across RF, because that current is going through RF, right? Which is going to be, whoops, hang on here. Which is going to be IS times RF. Let's put an RF, little F on here. That's the feedback resistor. That's the drop across RS. And so then V out is equal to minus IS times RF. And that's it. That's the relationship. RF is the scale factor. So sometimes this is useful if you have a sensor that's giving out, it has an output current of, 1 milliamp per, I don't know, degrees Kelvin, if it was a temperature sensor or something like that. And then you wanted to turn that into 1 volt or something per degree Kelvin. You could set RF equal to 1 kilo ohm, and you'd have 1 milliamp times 1 kilo ohm would give you 1 volt. Oh, I forgot the negative sign on here. So this is V out is equal to, oops, is equal to negative IS times RF. So this current to voltage converter does, this does invert the current polarity. So a positive current gives you a negative voltage. So if you have positive I, IS gives a negative V out, and a negative IS is going to give you a positive V out, right? So that may not be desirable. I'll show you on the next slide how you can use a technique called cascading amplifiers to putting 2 amplifier blocks together to get this so that it's not inverted. Or, in general, cascading is putting 2 or more amplifier blocks together to get you the overall relationship that you're looking for. Let's go take a look at that. But before we do, where does all this current go? If there's no load, or if there's like a super huge, a very large load here, RL, if it's so big that maybe it's, infinite, where does that current go? Remember that it goes into the supply, it goes into the output of the amplifier, into the output pin of the amplifier. So plus VS, and there's a minus VS here. And remember that all that current, at least in this case, is going to come into the output pin and then down to the negative supply voltage rail. All right, so let's then take, oh, where did that go? Oh no. I lost one of my slides, you guys. Hang on here. Let me just go and get that and retrieve that real quick, and I'll put it there for you. Sorry about this. Hopefully I can go do this fairly quickly. Somehow this didn't get into my, okay, there we go. Let's just copy this slide and come over here and, okay. So, you know what, I already have the, dang it, okay. Here, hang on. Let's erase some of this here. This is just kind of adding a little bit more detail than is needed. And so, yeah, so what we can do is, yeah, just redraw this here. Okay, so one of the things you can do, hang on. Getting weird behavior from my PowerPoint, it's not erasing things. Okay, so then let's go ahead and take a look here. So we've got that current to voltage converter that we just saw on the last slide. It gives out a negative IS times RF. That should be an RF there. Okay, it gives out a negative IS times RF. If you wanted that to become a positive IS times RF, so let's say you wanted V out to equal positive IS times RF, right? So that you had no inverting going on. The thing to do is use an inverting amplifier so that you can re-invert or undo the inversion of that had been done by the current to voltage converter with, in this case, we're going to do a gain of 1. If all you want to do is just re-invert it, right? So if you want a gain of 1, remember, you just let the feedback resistor in that amplifier equal the series resistor that's pulling from the source. So let R1 equal to R2. So in this case, you'll get V out is equal to a minus R2 over R1 times the signal that's feeding it. Okay, the signal that's feeding this thing is a negative IS times RF. And if you let this be 1, then you get that V out is equal to positive IS times RF. Okay, now, one of the things that it takes some getting used to when you see cascaded stages is realizing that, remember the amplifier, the op amp, before, what had to happen? Well, before we even connected the amplifier, remember that it had to take this current from IS and sink that down here, right? So we already knew that it had to take care of IS. But remember, the op amp will do whatever it has to. Op amp number 1, so let's label these. This is OA1 for op amp 1. This is OA2 for op amp number 2. Remember, op amp number 1 will do whatever it has to keep the voltages at its inputs equivalent. So Vn, so if Vp is 0 volts, then Vn must be 0 volts. And it will do whatever it has to maintain that. Now, speaking of whatever it has to, now it also has to provide a voltage to this R1 here. And it's going to, this is a negative voltage right here, this negative IS times RF. So if this voltage, if V, and the second op amp 2, we're going into like some deeper analysis here, just so that hopefully to help you see it better. But op amp 2 will do whatever it has to keep the inputs equivalent, which means that this is 0 volts. Vn is 0, Vn2 is 0 volts. And if that is 0 volts, then there must be current flowing from 0 volts down toward a lower negative voltage, IS, negative ISRF, that's less than 0. And so that current is then must be coming from the output pin. It's actually coming from the positive supply rail of that amplifier into through R2, through R1, and then into the output pin of op amp 2, or I'm sorry, of op amp 1. So op amp 1 is now sinking even more current than it had to in the prior situation. The prior situation where we didn't stick another inverter on there, where this was just a single current to voltage converter, and it was inverting. And all it had to sink before was IS, right? This current right here was IS. That's all that the op amp had to sink into its output pin. Now it has to sink IS plus the current coming from the second op amp. So remember, op amps will do whatever they have to keep their voltage, their input voltages equivalent. Okay. Let's then talk about the next type of amplifier, which is the summing amplifier. All right, so we're now going to derive the response for the summing amplifier by using the golden rules. Okay, rule number 1 is that IN is equal to IP is equal to 0. Rule number 2 is that VN equals VP. The op amp will do whatever it has to make VN equal to VP. Now this amplifier topology, this block, is called a summing amp because, as the name suggests, it sums or adds together the signals from different sources. You can have however many sources you would like feeding into a summing circuit. And so the sources here are shown as V1, V2, and V3 as these voltages. Let's pretend that these were signals. So here's signal, excuse me. Excuse me. It's, I don't know about you, but for me, it's allergy season. So I'm certainly dealing with it. Let's actually draw those signals on in a second, V1, V2, and V3. And for now, let's just note that they're voltages. V1, V2, and V3 are all different voltages. And so what we're going to do is a nodal analysis at Vn. You'll notice that most of the time, a lot of the times when we're deriving these relationships, we go and do nodal analysis at one of the input terminals. And oftentimes it's Vn. Again, reminder, don't ever do nodal analysis, a nodal equation at the output Vout, for reasons that we discussed earlier in this lesson. So let's do nodal at Vn. So here's what we'll do. This is V1 minus Vn over R1. That's the current coming in through here, right? We're looking at the current I1. Then we've got a V2 minus Vn over R2. That's the current coming through R2 there. Now we've got a V3 minus Vn over R3. That's the current coming through this guy here, and all of that is equal to 0. Whoops, no, I didn't get all the terms in there, and in fact, I'm writing too big to get all the terms in there. So let's do it again, because we didn't account for Vout. So let's do it again. So this is V1 minus Vn over R1 plus V2 minus Vn over R2. That's the current flowing through R2. Plus V3 minus Vn over R3. That's the current coming in through this guy there. Whoops, plus, then there's the current, if we're doing far minus near, Vout minus Vn over Rf. All of that is equal to 0. Okay, now by op amp rule number 2, so that actually is by rule number 1. We were able to take into account that there's 0 current flowing into the inverting terminal. So we accounted for all the currents going in and out of the node Vn. Now by rule number 2, Vp is equal to 0 volts. So then Vn by the op amp action is equal to 0 volts. So we can go ahead and set this to 0 on all of these terms. Okay, and if we do that and collect terms for V out and write it in terms of V1, V2, and V3, we find that this is the relationship. So notice that if I multiply through, do you guys agree here? What if we multiply through, we take this whole expression and multiply by RF, right? Oh, here, I'll just show the intermediate step for a second. Hang on. So then this would be, if we multiply by RF and then solve for V out, well, I think you can actually follow through on this with the algebra here, right? So this is V out is equal to minus RF over R1 times V1 plus a negative RF over R2 times V2 plus a negative RF over R3 times V3. Okay, if you multiply through by RF, you get an RF in the numerator on those V1, V2, and V3 terms. All right, so that is in fact the formula for a summing amplifier. We've just used nodal analysis and the golden rules to arrive at that. And what I'll say here is that this is, each signal has its own gain. That's the gain 1 for the signal V1. So gain 1 is equal to RF over R1. The second gain, the gain for signal 2 is RF over R2. That's this term here. RF over R3 is the gain for that term. You'll notice that they are also all inverting signals. So inverting gain, so the output is always inverted from any one of those signals. Let's now draw let's draw some signals on here for V1, V2, and V3. Let's pretend that we had a relatively low frequency sine wave going into V1. Let's say that we had a slightly higher frequency sine wave going into V2. Let's say it was about twice the frequency. And let's say we had a much higher frequency signal going into V3. What happened to my V2? Goodness, man. Let's say it was about twice the frequency, or maybe 3 times the frequency. Something like that. And then this one was, let's say, really high. Okay, let's say that's what it looked like. All right, the output voltage, V out, is going to look like the sum of all of those signals. So in the lab, if you wire up a summing circuit and you feed it different signals, the output of the amplifier is going to look like the addition of all those signals. So you'll see that it'll look like, and it'll be inverted, right? So you'll see the output will look like this. Here's due to V1, okay? But now we're going to superimpose on, that's V1 inverted. But now we're going to superimpose on top of that. And again, by how much of V2 is going to show up? Well, it's going to depend on the gain for gain 2, right? What that is relative to gain 1. And so we're going to see that inverted as well. So you're going to see this show up something, I don't know why this keeps doing this. You're going to see that show up something like this. Okay, and it adds on top of those signals. And then finally, when you add on gain 3, or the signal for signal 3, again, it'll depend on how much there is on gain 3. You're going to see that extra signal on top of here. And that is what the final output signal is going to look like. So if you wanted to see what the final output signal is going to look like, it looks kind of like that. Okay, you take those three signals together and add them up, again, by the factors determined by gain 1, gain 2, and gain 3. And that'll get you what, it'll get you the final output, okay? Now let's talk about some applications for summing circuits. They're used all over the place. Anytime you want to add signals together, which can be used in control systems and motor control feedback, it can be used in video signals, it can be used in adding signals together to do radio communications and things like that. It can be, this is an example, but you essentially would just apply the the algorithm here. So I guess we'll come back to the we can come back to the applications in just a second. But if you wanted to find this, realize V out would just be, in this case, it's -8 over. So if you're going to put this in here, right, it's minus RF over R1 times V1 minus RF over R2 times V2 minus RF over R3 times V3. Okay, and so, and this load resistor, it doesn't change anything about the summing circuit. It's just that the amplifier will now produce whatever current is needed through the feedback path, plus whatever current is needed through that 4 kilo ohm resistor to keep everything going the way, to keep that, you know, VP is equal to VN, but these are both 0 volts. So you can just plug in the numbers. This is, it's a -8 over 20 times V1, which is 1.5 volts, -8 over, looks like 10K times 2 volts, -8 over, looks like 6K times 1.2 volts. And that'll tell you what V out is. So we would now have V out. If you wanted to find the output current, trying to write a check mark, V out is equal to whatever the value is. If you wanted to find the output current, I naught, let's just do that in green over here. I out equals what? Now what you need to do is do a KCL at V out. And so you know that you've got, if this is, if you know V out, you know how much current is flowing through the 4K, right? So let's say that, just for discussion's sake, let's see, do I have the answers written here? Okay, the answer is V out is -3.8 volts. Okay, so now that we know that V out is, this is -3.8 volts, that means that there's current flowing up through the 4K resistor. That's going to be -3.8. So that's -3.8 over 4K, which is 0.95 milliamps in that case. So this is going to be 0.95 milliamps flowing through the 4K. There's also going to be current flowing through the 8K from 0 volts. Notice that that's going from 0 volts down to a negative voltage. So that current is going to be 3.8 volts over 8 kilo ohms, which is 0.475 milliamps. And notice that both of those are feeding into that junction. So I out must actually be going the other direction, right? So I out, the magnitude of it anyways, is, it's to the left, is going to be this 0.95 milliamps plus 0.475 milliamps. And when you add those together, so plus 0.95, we get 1.425. So I out is equal to 1.425 milliamps to the left, or I out as drawn is negative 1.425 milliamps as drawn on the schematic. Okay, so since like when I ask questions in the Canvas quizzes and things like that, you have to you know, provide the direction. I always do that by showing a sign. So at any rate, that's an example of the summing amplifier. Let's talk about applications. As I mentioned, there's video, radio applications, motor control, anytime you want to add two signals together. And one of my favorite summing applications is a giant mixing console. And there's yours truly at Skywalker Sound up in Marin at Lucas Skywalker Ranch, George Lucas's studio. A friend of mine is an audio engineer that does some work there, and he finally brought me there after I'd asked him for years. They've got a giant mixing console, and that thing takes signals from microphones out, and they record orchestras out there, and they win Grammys at this stuff they're doing, or at least get nominated. And and the every fader on every volume control on the draw this in red here, it might show it better. Every one of these faders controls the level of an audio signal. And so here's a much smaller mixing console that shows that same concept. But if you ever wondered how such a device works, you now have studied the electronics, the basic building block behind that, is that each channel has a small fader on it. Well, I shouldn't do that in red because I'm color coding this here. But the fader shown in blue is a variable resistor. And so that is that's shown here, where you're adjusting as you move that fader around, you're changing the resistance. Remember that the gain V out is equal to, you know, negative RF over, let's call that in blue, oh, bright blue, R1 here. And as R1 changes, and then that would be times V1 or whatever, the signal feeding into that, maybe that's the bass drum or, you know, a violin or something like that. And then you mix and add on to that. This would be plus a negative RF over, and in this one, this would be green, R2 times V2. And let's say V2 was another signal. Maybe it's the tambourine or a, you know, a hi-hat or whatever it is. And those two things go to the output stage, where the output stage is shown here in this fader. That's RF, and then this is grounded. So that's ways in which that works. If you're interested in audio, you know, production, and you've heard about the advent of people working in a digital medium, shown in the left is a common audio recording platform called Logic Pro X. If you've heard of Pro Tools or other things, but anyways, you have a bunch of digital audio files, and you can mix them together by numerically adding the ones and zeros in that file. Or as people have started to come back to do, because they value analog circuitry and sound and signals running through real electronics, there are sonic differences. Sometimes people will send all those signals out of a digitally recorded platform and into a mixing board or a summing amplifier, which is shown down there. That's a summing amplifier. It's kind of a condensed version of the mixing board we just saw. So what I'd like to do in our last couple of moments is discuss the difference amplifier. Okay, so the difference amplifier is shown here, and we're going to solve what this circuit does first by the golden rules. Okay, so by the golden rules, if we do a nodal analysis at VA, all right, so the difference amplifier has two signals, V1 and V2. And it has four resistors, R1, R2, and R3 and R4. And it produces an output voltage that is equal to some kind of well, we'll see what it's equal to in just a second. But it produces an output voltage that is equal to some difference of V1 and V2. So if we do a nodal analysis at VA, we get a V1 minus VA over R1 plus a V out minus VA over R2 is equal to 0. And what we're going to do is multiply that whole thing by R2. And now by the op amp action, well, we'll multiply this whole thing by R2 in just a second. Hang on. Before we do that, let's talk about by the op amp action. In other words, rule number 2, VA is equal to VB. So these two voltages are identical. So VA is equal to VB, and VB equals, notice that R3 and R4 here form a voltage divider with V2 because there is no current flowing into those, to that input pin. So this is equal to V2 times R4 over R3 plus R4. And now what I'm going to do is plug in, if I multiply this thing by R2, okay, so I'm going to take the first equation we wrote by R2, and I solve this for V out. I'm going to get V out is equal to 1 plus R2 over R1 times VA minus an R2 over R1 times V1. Okay, now we want to have this V out in terms of V1 and V2. Okay, so so this whole expression for VA is going to go down into here. And if we then plug that in for VA, we arrive at the general expression, the general case for a difference amplifier. Here it is. V out is equal to 1 plus R2 over R1 times, here's us plugging in for VA. This is R4 over R3 plus R4 times V2. Okay, that was us plugging in for VA minus an R2 over R1 times V1. All right, this is the general case. The general case. Okay. Now, just to practice using superposition, I'd like to show you how you could analyze. You could do this same analysis by superposition. Okay, so you could say that V out due to V1 is if you turn off V3, that's not actually super apparent. You know what, let's come back to looking at this by superposition another time, because I'd need to redraw these circuits for you to be able to see it. So let's come back to that another time. But what I'd like to do before we end today, I really want to finish this off, so I'm going to go just a couple of minutes, so this will be recorded on the video. If you have to take off at this very moment, I understand, no worries. But please do stick around if you can. It'll take a couple minutes, 3 minutes, to just arrive at the special case for the differential amplifier, which is one where we often want this to work. And many times, instead of this general case where there's this long expression, you'll notice that there's some kind of, if we were to look at this, there's some kind of term times V2. There's some coefficient times V2 minus some other different coefficient times V1. Sometimes that's what you want. Like if you wanted a V out is equal to 5V2 minus 2V1, then you could design a circuit that way, and that's fine. A lot of the times we want something where we would like V2 minus V1 times a single gain. A single differential gain. All right, so so that's called, this is a special case. That right there is the special case. And the question is, what does G equal? How do we get, what resistors do we pick so that we get a single gain? And what is that gain in terms of those resistors? So what we'll do is we'll take the general case. That's V out is equal to, well, I just wrote it on the last page, but we'll write it again. R2 over R1, 1 plus R2 over R1, that quantity, times R4 over R3 plus R4 times V2, minus R2 over R1 times V1. Okay, and what we're going to do is, if we want these two things to be equal, a single gain, so we want a single gain, we want to make these equal, okay, then what we're going to do is impose that those two terms are equivalent. So 1 plus R2 over R1 is times R4 over R3 plus R4 is identical to R2 over R1, the magnitude of that second term. Okay, we're going to do a little bit of algebra over here. I'm going to move, so I'm going to do a couple of swift moves. I'm going to take R2 over R1 and I'm going to move it over to the other side by dividing it down into the denominator. And simultaneously, I'm going to take this term, R4 over R3 plus R4, and I'm going to move it over here by taking the reciprocal of it. So when we move that other term over, we've got the reciprocal is R3 plus R4 over R4. And then this will be a 1 plus R2 over R1 over over R2 over R1. Aha. So what we get then, if I rewrite this, is that this is a R1 over R2. Notice that these, the R2 over R1 cancels here, and then the 1 over R2 over R1 becomes, or they don't cancel, sorry, they become a plus 1. And and this R1 over R2 in the denominator flips and becomes R1, I'm sorry, R2 over R1 flips to become R1 over R2. And this right here, this R4 over R4 is a 1, plus the other term, R3 over R4 is here. And we're almost done. Thanks for hanging out with me, for those of you who could. Where these are gone, the ones cancel. And what we're left with is that R1 over R2 is equal to R3 over R4. That is the that is what you have to impose to get the special case. So to get a single gain, G times the difference of V2 minus V1, G is equal to R1 over R2 as long as you maintain the ratio R1 to R2 is equal to the ratio of R3 to R4. So if you encounter a differential amplifier that has those, it looks like this, where there's 4 resistors, but the ratio of R2 to R1, let's see, of R1 to R2 is the same as the ratio from R3 to R4, you don't have to use the general case formula. You can go and use the final formula. So this would be then if I was to write this out, this would be V out is equal to R1 over R2 times V2 minus V1. That's a much nicer formula to use if you have the special case here. Okay. Also, if you were designing a differential amplifier that had a single gain, what you can do is pick the gain using R1 and R2, and then just choose a ratio of resistances R3 into R4 that are the same. So with that, I just want to direct your attention one last time to the Canvas page, where I would like for you to go to, in the modules, go to the op-amp section and click this link to watch these videos on differential amplifiers. I did not get to talk about more about cascaded circuits. I'll finish that next Tuesday when we meet. But this video here is going to
welcome back to
walk you
Engineering
through a few. Hang on here, just let me. This is going to walk you through designing a difference amplifier of certain values, and this one is first using the general case. Then it's doing this again with, let's see, this is using a cascaded op-amp circuit. So if you wanted to, so this will walk you through designing it with a cascaded op-amp circuit. You could look at cascaded op-amp circuits beforehand if you wanted to as well. Okay, thanks everybody for spending a couple extra minutes. I really appreciate it. And it was great as always to connect with you. Enjoy your day off on Thursday, and look out for that homework assignment on op-amps I'll be posting later today. See you next time.
Thank you, Professor.